Good morning, good evening, good afternoon, wherever you are around the fourth world. By way of introduction, I'm Bill Ragsdale, the founding president of the Fourth Interest Group and the first chairman of the standards team back in 1978-79. But that is all ancient history. Today we're going to talk about a very interesting topic on using Fourth to work on calendar calculations and determinations. First, a bit of a caution. We're going to cover a huge amount of material today, and so do not focus so much on the code itself. A lot of the code is very mechanical, very mathematical. Instead, let's follow the concepts, because those are the elements that will guide you in the future. We'll give you some archive locations on the next slide, which will be very helpful, because the full slides on this and video are going to be online. The video will be in YouTube, and the slides will be on GitHub, and they're also referenced in the Fourth website. So it's an amazing thing that all of the Fourth Interest Group presentations, handouts, slides, 12 meetings a year for 24 years are all archived, and they are at fourth.org. You go halfway down the screen and you go to a Silicon Valley Fourth Interest Group. About half the way down on that, you'll see the lines for the past meeting slides, videos, and notes. The slides and PowerPoints are all there, and there will be links to all the videos. It's very, very well archived. And also, my presentation today will be posted at GitHub. The slides and source code will be posted. This material is golden. I emphasize, here is a 24-year archive. Through it you can follow the progress of Fourth from the late 1990s to the current date. So let's go on to the topic for today. The challenge we have is to program the ISO 8601 standard week. ISO 8601 covers date representations, time representations, primarily for computer use, but it also specifies the week numbering system. And particularly in Europe, this is used for business, finance, and company operations. For example, they might say that we'll do a survey in week 3, we'll do a plant visit on week 5, we'll do a budgeting on week 6, and so on. And since everyone has week numbers on their calendars, they know immediately when the activities will take place. For a number of years, I published a financial newsletter, and all of our issues were keyed to this week number. So the way an ISO week is structured, it begins on Monday, and the weeks are numbered from 1 to 52, or about every 5 or 6 years, there are 53 weeks. And the key element is that week number 1 is the first week containing Thursday of the year. We'll see that the weeks may overlap between following and prior years, and that's where it gets a little bit tricky. So our challenge is to program the ISO week for any date. We'll be using what's called the Zeller rule, which is a calculation fashion to determine the day name of a given date. And you can also check your results by Excel, because they have ISOWEEKNUM added in as a function. This was added about 10-15 years ago, and I tried to program it myself with no success. Along the way to this ISO week numbers, we're going to use a number of tools that are used for calendar support, and this will allow us to make that final calculation. The key to all of this is Zeller's rule, which allows us to find the day name of any date. It's very Fourth-like because it uses integer arithmetic and round off. All the information is integer and the fractions are rounded. It is tricky, and you'll see I've got a systematic approach. I hope you'll pick up on it. As utility, I wrote a couple of words. The first one is to accept a day number in numerical form. So the word accept queries the keyboard to say, give me an input day number. We get the day, we get the month, we get the year. These three words, get day, get month, get year, do range checking. So that's why they're separate. It's an example of the use. We key in the word accept, and we put in the day number 26, month 10, year 2023, and that was the day I did some testing on this. The report word will apply this entire process. It will query for a day, and it will return the day name, which in this case was Thursday. Starting point is we need to isolate and react to the leap years. We all know and understand those. The formula of this is that if the year is evenly divisible by 400, it is a leap year. And if it is evenly divisible by 4 but not 100, it's also a leap year. A couple of examples: 2000 is a leap year because it is divisible evenly by 400. 2001 is not a leap year because it is not divisible by 4, and it is not a leap year. 1900 is not a leap year because it is divisible by 100. This is the calculation, pretty simple, what we're used to in modular arithmetic. We take the year, we do the 400 calculation, we do the 400 calculation, we do the 100 calculation, and then we combine those two with an and an or at the end, and we'll get a true flag for leap years. Here's a test on that. We take 2000 and query that and say, is it a leap year? We get a -1, which is a true flag. We go to 2001, is that a leap year? No, it's not a leap year because we got a 0 result. To put this into some use now, we need to be able to locate the leap days. So I've developed an array here. The first portion is 12 bytes long, 1 byte for each month, and it simply contains the number of days in the month. The first entry is 31, which is January, 28 is the second entry, which is February, 31 is March, and so on. Then there's a second sequence of 24 bytes, and notice in this case the second entry is 29, which is February in a leap year with 29 days. To be able to select from that array, we have a simple word called day array. In this case, we access that days per month we just saw, do a check to see if it's leap year. If it's leap year, we add 12 to it, which just gets us into the byte array at the leap year portion. As a test on that, 2001, we apply a day array to that, and we get the address ending in 5656, which is not a leap year. And then for 2000, which is a leap year, we get the address ending in 668, which miraculously enough is 12 bytes later. Next, we want to know the number of days to a date. So in this case, we are scanning across the year, and we add up the number of days cumulatively from that array, so we will get the number of days in the prior month, and then add the day number of the current month, and that will get us the days to the date. Notice also that this results in calculations that are 0 based. So January 1 is 0, and on a non-leap year, December 31st is day number 364, and we know in that sequence there are 365 elements. So to do that calculation, first we take 0 and do a dash rote, which sticks the third element down. Do some simple manipulation to develop the range limits, and then we do a do loop which scans across the array. And then of course at the end we have the summation, and we do a -1 because again this is 0 based. So let's do a little test on that. Days to date, remember January 1 is day 0. So the first line is 1/1/2001, days to date, and we see a 0 because that is the 0th day of the year. A non-leap year of 2001, last day of the year is 364. 2000 on the third line is leap year, so again we see a 0 as the first day of the year, and then for December 31 we 365 days, and which we know is the 366th day of the year. Now we get to the Zeller rule, which is a fascinating thing. It allows us to calculate the day name of any date in the year. So if we wanted to know the day name of July 4th, we would apply the Zeller rule, and it will come back and give us the number that corresponds to that particular day of the week. The Zeller rule uses a funny organization of the years because it begins its calculation on the first day after the leap day. So it goes to a year with a February 29, and the next day following that is its day 0. It continues for 4 years, ending on the next February 29th in leap year. This can cause a bit of confusion because you have to start thinking in the months with the offsets back and forth, and it took a little while for me to get used to that. Here's the full example. We see the Zeller year of 2000. It began on March 1, 2000, and it goes 365 days, ending in February 28th of 2001. The next year goes to 2002, the next year to 2003, and finally the leap year comes along, and it ends on February 29th of 2004, which is that last 1461st day of the sequence. In order to accomplish this, the Zeller adjusts the month numbers, and in it the months start at March, which we would realize from the prior information, and it continues through December as the 10th month, and then goes into the following year as the January 11 and February as the 12. So we see that at the beginning of any year, the first 2 months are a part of the year before, and the year extends into the following year. So as I just said, the adjustments for January, February use the prior year. This is an example of those adjustments. Notice that for January and February, the traditional numbers are 1 and 2, but in green are the Zeller numbers, 11 and 12. And for year 2004, the months of the first two, January, February, are actually from the prior year, 2003. It's a little bit confusing when you first calculate it, but then again, once we put a couple of fourth words on it, this inconsistency disappears. The adjustments for a year is we start with the month and the year, and we generate what I've noted as ZY, which is the Zeller year. And this just looks at the first 2 months, and looks at the year number, and sees if the month is 1 or 2. If it is, it subtracts 1 from the year. So for January, February, 1 is subtracted from the year, and we get the Zeller year. To adjust the month, it's a little less obvious, but in this case, what I worked out was to add 10 to the month, compare it to 12. If it's greater than 12, then subtract 12. And miraculously, that does the proper adjustment. Now the Zeller rule itself. We begin with the day number. So for example, July 4th, we begin with the number 4. Then we take the adjusted month, and in the case of July, 7th month, it would actually be month 5. And it's multiplied by 26, 2 is subtracted and divided by 10. Why? I don't have the slightest idea. We then take the adjusted year, divide by 100, look at the remainder. This gets us the lower 2 digits of the year. Then we divide that by 4. This gets us into which is a leap year. We make an adjustment for the 400. We make an adjustment for the 200. Add them all together, subtract the last value, take a modulo 7, and we then get the Zeller day number. When I programmed this for error checking, I took each factor and wrote a word around it. So I have factors A through F, and the first one you see is very simple. It is just day. The factor B is the adjusted month, multiplies by 26, subtracts 2, divides by 10. So every one of these corresponds to one line in the prior sequence. These factors are added together, 5 are added together, the sixth factor F is subtracted, and then 7 mod gets us the conclusion. I factored these out for error checking, and you'll see one of the references at the end gives us 3 worked examples separated out in these 6 factors. So by using that sequence from the reference list, you can get step checking. It'd be pretty involved to error check that as one complete function with 6 components. We see we get to the bottom of a sum, the sum is 39, divide by 7, we get the day of 4. Some of these summations come to be negative numbers, so we're doing modulo of negative numbers, and fortunately most fourths get this correct. I'm not sure about older fourths and some of the most primitive, but all the new fourths seem to get modulo of negative numbers correct. This is a simplified Zeller rule. We just stripped out all the comments and organized it in a little briefer fashion. So you see it's pretty mechanistic. We start with we adjust the year, we adjust the month, we go through the calculations, all those modulo and divisions, come down to 7 mod at the very end, and that gives us the day number 0 through 6. Let's test those. The first was October 26, 2023, the day I did this programming. Sure enough, it was a Thursday. Then we look at July 4th, 1776. This is the founding day of the United States of America. And sure enough, it was Thursday, just as we all know. And finally, December 7, 1941. This is the day that shall live in infamy, the day that Pearl Harbor was bombed. And we know from our history lessons that it was early on a Sunday morning. So now we're up to the week number itself. Using all of these tools up to this point, we're now going to determine the number of days between the first Thursday of the year and the Thursday of the week of our target day. Notice that these all key off of Thursday because that is the day that determines the first week of a Zeller year. So again, we are going to determine the days between these two Thursday dates. Then we divide by 7 and add 1. We divide by 7 and we get a week number that is 0 based, but again our tradition here is that we use weeks that are number 1 based, so we have to offset by 1. Next comes an adjustment for the first and last week of some years. This is tricky, and it took me tinkering for the better programming effort over a couple of days to finally resolve the methods. There are about 3 different ways to calculate this, and a number, of course, of steps that took me to discover them. Here's the pseudocode for determining the week number. We start with the day, month, and year, and we want to end up with N, which is the week number. So first we find the day number of the target day. Imagine that we're doing July 4th, 1776. We want to know that this was a Thursday. So that test gets us to the number for Thursday, which of course is a 4. Then we find the number of days in the year to that particular target day. And then we calculate the offset within the week from the target day to Thursday. It could be a Sunday in case we're incrementing forward. It could be a Saturday in case we're incrementing backward. Once we determine that offset, we apply it to the year, to the day of the year position. So now we've taken our given day of the year and we shifted it to find the equivalent Thursday position in the same week. We then find the days in the year to the first Thursday, subtract the 2, this gets us the number of intervening days, divide by 7, and add 1. This gives what I call the raw week number, and we're not quite there yet because we have to possibly make adjustments for the first and last week. This is a little code clipped out of that former definition, so we see the interior part of finding the target Thursday, and that is we do 3dup, which duplicates all 3 day, month, and year. We make the day check, we save that. We then do a days to date and then recall the day value. Now we're doing some arithmetic to offset to Thursday, and this gets us then the number of days we have to offset our day of the year by, and we negate that and then add. Now this has got us now to the position of the target day within the year relative to a Thursday. Then we need to find the first Thursday of the year. In this case, we know it's in the first week. It's between the first and 7th day of the year. So first we find the day of the date, and then we set up the do loop range and find that day of the date and see, we're scanning from 1 to 7, and we're seeing then, is the particular day 4? If so, we drop the input value, and we get the loop index and leave. So in this case, we scanned across the first 7 days of the year. We found when we get a 4, and then that position is returned. So that is Thursday's day number, first Thursday of the year. So this is the final process where we save the year, we find the day of date, days to the date, we do that Thursday adjustment, we locate the first Thursday, we subtract, add 1, and now we come to the part of adjusting to get the week number. So here's what the offsets look like on the first and last week. In January 2010, it turns out the first week of the year is numbered as week 53. It's not actually the first week of that year, it's the last week of 2009. So we see 2009 ends with 29, 30, 31, and then it blends into the 1st, 2nd, and 3rd of January the following year. The date with the green arrow can either be a 52, a 53, or a 1. The same thing happens at year end. Now we're looking at December 2014, and we get to the end of the year, and we've hit the 27th and 28th. We get to the following week, which is the 29th, and it is not the 53rd week of the year, it's day 1, it's week 1 of the following year. And so again, this could be either 1, it could be 52, 53, or 51. The raw week that I mentioned for the last week adjustment, if it computes to 53, it could be a 53rd week, or it actually could be week 1 of the following year, and that's what we need to determine. If the target day of the rule is this: if the target day of the week is less than 4, that is, it's Sunday through Wednesday, it's before Thursday, and the raw week number is 53, then we force the week number to 1. So if we have a fragment of the week at the beginning that does not contain a Thursday, it actually is forced to be 1. It's not a 53rd week, it's the first week of the following year. The first week adjustment, if our raw week comes out as a 0, it tells us this is a partial week of the prior year. So how do we accommodate that 0? Is it a week 52 or a week 53? In the prior year, we make the test. Notice we step back to the prior year because we're looking at the last week of the prior year, and we test, is the last day of the year Thursday? If it is, we force a 53. Or is the last day of Friday and it's a leap year, then we force 53. Otherwise, it's 52. There's a couple of different ways to calculate this. This one is the most obvious. So we're looking at the last couple of days of the year, and we're finding out should that last week be a 52 or a 53. So this is the calculation that's done. First we save, the N1 is our raw week number, we save it. We then test first for week 0. So the 0 equals if, says yes, it is a 0 week first. We then do this Thursday, Friday leap year test, and if we pass that, we then drop all 3 day, month, year. We drop the stored week number, the raw week number, and we force a 53 and exit. Otherwise, we again drop those parameters, force a 53 and exit. If this is not the case, then we test for a week 53. If it's a week 53 and the target day is less than 4, meaning it's a Sunday through Wednesday, and the week is a 53, then we do an R from drop, which drops our raw number, and we force a 1 in and exit. If none of these happen, The R from just recovers our raw week, and we continue ahead. Each of these is a fairly simple test, but I assure you in developing these, it was a significant, I mean, several hours of study, tests, and so on to develop each component. Quite a challenge. To look at the code altogether as you might program it, you can see there's phrases to it. The first part is we're calculating the day of the date, then days to the date, we're doing the first Thursday, we do that little bit of arithmetic, we do the week adjustment, and we are done determining the day number of any week, the week number of any day. I wrote a test routine on this to make sure that I was covering the bases, and I happened to have printed calendars that showed the week numbers from 1994 to 2026. So I extracted from those the first value of January 1, which is in the want column. In the second want column is the last day of the year, December 31st. And then for each of those weeks, the GOT shows what it should be. If there's an error, an arrow will pop up and it will point to the row that has an error. And sure enough, going through all of those sequences, we find that the function is operating properly. So as a conclusion, I tried to do this years ago because I was using it in business, and I was unsuccessful. I tried it in Excel, and I did not know this trick about taking the days between Thursdays and dividing by 7. I was trying to find my own commonality between these, and I was not successful. And I also explored into Visual Basic for some of the calculation. I'll point out that most smartphone calculators can be adjusted to set Monday as the first day of the week, and that's what I do on mine, because to me, the work week is Monday through Friday. Saturday, Sunday should be contiguous because you have a different activity level on the weekends, and I show the week numbers. On some calendars, you may find that they actually show week numbers, but they show Sunday in the first position, and that is incorrect. That Sunday is actually part of the prior numbered weeks. If you were using this in a sincere way, you need to know that that first Sunday is part of the prior week. So here we are. We've accomplished examining the year, getting familiar with the calculations, developed a number of words to support that, and we've come up with ISO week numbers. The key reference I found was this beginnersbook.com 2013-04, because it gives a beautifully worked example with 3 examples, and it's factored just as I've done in my code. As I mentioned at the beginning, all of this material is going to be archived at forth.org under the Silicon Valley, and then for the meeting slides and meeting videos. And again, this is a goldmine of information. And finally, all my information is going to be posted at GitHub, which will be source code and the slides. So thank you very much. This is Bill Ragsdale saying thank you so much, and we'll now return to Kevin, and thanks for your rapt attention.